let's complete this exercise today. So you already know how it starts. We have a ring homomorphism F from the ring A into the ring B. I1 and I2 are ideals of A and J1 and J2 are ideals of B. And this time, this is what we have to prove. The extension of the quotient I1 colon I2 is contained in the quotient of their extensions, I1 extension colon I2 extension. So we start the solution by taking an element x in, well, not in the extension itself, but in this quotient ideal, I1 quotient I2. Then by the definition of the quotient, x I2 is contained in I1. Next, let us take some finitely many elements in our ring B, y1, y2 up to yn, and an equal number of elements in the ideal I2, a1, a2 up to an. And we consider this product for all these elements. Outside we have f of x, and in this sum, I call it a product because it is f of x times something, right? And that other something is a sum of all these products yi f of ai as I varies from 1 to n. Alright, why did I suddenly take this? We will see. But let us first see what it becomes. It becomes this. How? There are some intermediate steps which I have not written. See, first of all, you are able to apply the left distributive law in your ring B. Using that, you can take the f of x inside. So it gets inside and it gets multiplied with all the terms of the sum. So the next line ideally would be summation f of x yi f of ai. And then you can change the position of f of x and bring it inside more, because all your rings are commutative. So the ring B is also commutative. So you can next write yi times f of x times f of ai. But f of x times f of ai is f of x times ai, because f respects multiplication, f is a homomorphism. So that's how we get this. Now what is this? I mean, what can you say about this term? This is what you can say about it, that it belongs to I1 extension. How? You consider this containment. X times I2 is contained in I1. So that means that if you take any element from I2, multiply that by x, that is in I1. In particular, for these elements, these AIs, which are elements in I2, x times ai being in xi2 is also in I1. And that is why all these x AIs that you are seeing are elements in the ideal I1. And this is how a general element in I1 extension looks. That is why it belongs to I1 extension. Alright, so that means this product belongs to I1 extension. Now you look at this product. Now we come back to that question of why we considered it. Well, what do you see in this sum? In this sum you see a form, the general form of the elements of I2 extension. Why? Because all these AIs are elements in I2, and this is how a general element in I2 extension looks. That is why what you are looking at here is f of x times any element in I2 extension. That is inside I1 extension. So f of x times I2 extension is contained in I1 extension. And now this containment will tell you something immediately. So this is what you immediately get from this one. Thus, f of x is an element of this quotient ideal, I1 extension, quotient I2 extension, because f of x being an element here just simply means this. This is the definition of this quotient ideal. But now you go back and see where x is coming from. X was an arbitrary element of this quotient ideal, and its F image is an element here. So the F image of this entire ideal is contained in this. But then by the definition of the extension of this ideal, this will be contained in this, and that's what we wanted to show. And next we have this one, which involves contraction and the ideals J1 and J2. The contraction of J1 quotient J2 is contained in the quotient of J1 contraction and J2 contraction. To prove this containment, we take an element x here. This time we don't take an element in just the quotient. We straight away use the entire contraction, because contractions are very easy. They are just inverse images under our function f. So let x belong to this. So, and this means f inverse of J1 quotient J2. But if x belongs to the inverse image, then by the definition of inverse image, f of x belongs to this quotient ideal J1 quotient J2. Or then we use the definition of this. So f of x times J2 is contained in J1. Okay. So we are going to use this. Now next what we do, we take any element b in J2 contraction. And J2 contraction by definition is just the inverse image of J2 under F. So B is in this inverse image. So F of B will be in J2. Okay. And that is why for that x and this b, if we now calculate f of xb, first of all you can split it like this, f of x, f of b, because f respects multiplication. Now f of b belongs to J2, and that's why f of x times f of b belongs to f of x times J2, which is contained in J1. So ultimately what are you getting from this? You are getting the fact that f of xb is an element of this and hence an element in J1. But if f of xb is in J1, then xb will belong to the inverse image of J1 under F, which by definition of contraction is J1 contraction. And then we have this. Because xb belongs to J1 contraction and b is any element in J2 contraction, so x times J2 contraction is contained in J1 contraction, which implies that x belongs to this quotient of J1 contraction and J2 contraction, because that's just what it means. But what was x? X was an arbitrary element of this contraction, and we have found that it's also an element here. So that's how this is contained in this. There are two more statements to prove. The next one is this. R of I means radical of I. The extension of that radical is contained in the radical of the extension I extension, where I is obviously an ideal of A. So we start our solution by taking an element x in the radical of I, not the extension. Okay, we do that for contraction. For extensions, we just take the thing whose extension we are taking. So x belongs to the radical of I means what? You recall what radical means. It means that some power of x belongs to I where the exponent is some positive integer. N, say x to the power n belongs to I. Okay. Now next what we do, we consider the nth power of f of x. So this is f of x to the power n. Because f respects multiplication, it's the homomorphism. So that equals f of x to the power n. And that's why, because x to the power n belongs to I, this belongs to f of I. But f of I is by definition of extension contained in the extension of I, is a subset of IE. So this f of x to the power n, which is just this, will also belong to the extension of I. But what does that mean? It means that f of x then belongs to the radical of the extension. Because some power of f of x is inside the extension, so f of x by the definition of radical will belong to R of IE. But what is f of x? X was an arbitrary element of R of I. So f of R of I is contained in R of IE. But if this f image is contained in this, then by the definition of the extension of Ri, that would also be contained in this. Why? I mean, you recall the definition once more. This extension is the smallest ideal of the ring B containing this set, and this is some ideal in B containing that set. So that smallest nature makes this one a subset of this. And finally, we have this equality involving contraction. The contraction of the radical of J is equal to the radical of the contraction of J, where J is some ideal of the ring B. Because this is an equality and not merely a containment, we have to prove that each side is a subset of the other. Let us first show that this is a subset of this. So we take any element x in this contraction, and the contraction by definition is just the inverse image of radical of J, and x is an element in that. So then f of x will belong to the radical of J, but then by the definition of radical, some power of f of x will belong to J, where n is some positive integer. Okay, now you concentrate on this f of x to the power n. Because f is a homomorphism, this will be equal to f of x to the power n, and that you already know belongs to J. So this f image is inside J. So x to the power n will be inside the inverse image of J under f, which by definition of contraction is just J contraction. But then some power of x, where the exponent is a positive integer, belongs to the ideal J contraction, and that's why x will belong to the radical of J contraction. So that way any element here is also here. So obviously the conclusion will be that this is the subset of this. So we write the conclusion here, hence Rj contraction is contained in R of J contraction, and then we prove the reverse inclusion. For that we take any element, let's call it y this time. Let y be any element here, R of J contraction. Then by the definition of radical, some power of y will belong to J contraction. Let the exponent be m. If you want, you can use n again, because it's just a variable for some positive integer n. But what is J contraction? J contraction is f inverse of J. Y to the power n belongs to f inverse of J, so f of y to the power n will belong to J. But f of y to the power m is equal to f of y whole to the power n, because f respects multiplication. And then next we have this f of y belongs to R of J. Why? Because some positive integral power of f of y belongs to J. So by the definition of radical, f of y should belong to the radical of J. But that means y belongs to the inverse image of R of J under f, which by definition of contraction is just the contraction of R of J. So that way you see that any element in here, R of Jc, is here, the contraction of R of J. So that is why this is also a subset of this. Combining these two containments, you have equality.